Hello everybody, welcome to a short presentation on production logging. First, let me introduce myself. My name is Ahmed Elsherif. I joined Schlumberger Oilfield Services in 1981, straight away after university. I've graduated from Cairo University, Electrical Engineering. I have done several years in the company, moving from one position to the other, from field to interpretation to personnel to... The main importance of production logging is to monitor the performance of the well and see how much flow is coming from which perforation in the well. Now, once we get this flow profile of the well out of production logging interpretation, we should decide whether the well is producing as per expectation, or we need to do some intervention to improve the well performance, like removing extra water production or gas production or so on. Now, let's talk about different sensors that we have inside the production logging tool. First, let's talk about the auxiliary sensors, which include first, CCL, which is very important so that you'll be able to see exactly the color of the joints inside the tubing or inside the casing. This is very important for depth matching, and if you are planning to set a bridge plug in the future, you should not really put it across a collar in the casing there. Second sensor that we need to speak about is the gamma ray. Gamma ray is very important for depth matching. We need to make sure that our logs are depth matched to match the open hole logs that we have. The third sensor that we have inside the tool is the hole deviation. Hole deviation is very important for some of the sensors, as you will see during this presentation. Last but not least is the caliper measurement. Somebody might ask, why do I need a caliper if I have cased the hole and I know the casing ID? I agree with you. If you have a brand new casing, a brand new well, then fine, you don't really need a caliper. But if you have an old well where you expect to see some wear in the casing ID or scale deposition inside the casing ID, then you really need a caliper there. Now, in order to calculate a flow rate, you need to have a fluid velocity inside the casing that you have coming from different perforations. Now we have different sensors that take care of measuring the flow velocity inside the casing. The first one is the spinner, which is the most used tool in the production logging, and I would say that 60 to 70% of the answer product is coming from the spinner response. That's why we should be very careful when we are planning and running and interpreting spinner response, as I will elaborate more very shortly. The second sensor that we can have inside the production logging to measure the fluid velocity as well is what we call the PVL, or phase velocity tool. This tool is using a specific material that emit inside the borehole. This material is not toxic, not radioactive, and it's like gadolinium, so it can be dispersed with either the oil or the water, and you can see the effect of that by introducing high neutron with very high speed coming from the minitron inside the tool to measure the effect on this material, because this material has a very high sigma capture cross section. The third tool that can see the fluid velocity is the tracer ejector. This tool is very similar to the second tool, but instead of emitting a harmless material, we are really injecting a radioactive material, which is a little bit dangerous. And by placing different gamma ray sensors, we can calculate the time it takes for this radioactive isotope to travel from one point to the other and calculate our fluid velocity. Of course, most of the people in the field will be very much reluctant to run this tool in a producing well because you are using radioactive material there. Last tool, but not least, is what we call the oxygen activation, where we emit fast neutron from the tool through a minitron, and we activate the oxygen atom inside the fluid there, and the only fluid that has oxygen will be the water. So this tool will be responsible for measuring the water velocity, and that's why we call it water velocity log. Now let's go back again to the first sensor, which is the spinner. So what is the spinner? Spinner is a tool with a centralizer, and you have blades inside rotating as per the fluid velocity that it's passing through. The response of the spinner blades is proportional to the relative speed between the tool movement and the flow inside the borehole. We have three different types of spinner tools. We have what we call the continuous flow meter spinner, which is flow meter with OD of 1/1116 with small plates inside of 1 inch, and this tool can read inside the tubing and inside the casing. Continuous measurement of flow inside the tubing and inside the casing. This is good because you can see everywhere, but this is bad because the blades are so small. So if you have very low flow rate, you will not be able to calculate a proper flow rate with good accuracy. The other tool that we have is what we call the full bore spinner. Full bore spinner means that you are sampling the full bore with this spinner. This spinner blades can go up to 5 inches. Now somebody might ask, how can I run 5-inch blade inside the tubing with restriction of down to 2 inch or something? Now these blades are run collapsed like this or like this. Once you're running the hole with the spinner collapsed, you cannot read anything. The spinner cannot rotate. Once you pass the tubing shoe, the spinner will start to open and will start to rotate and will be able to get measurement below the tubing shoe. So the main advantage here is that you are sampling a large portion of the fluid so that the sensitivity and the resolution is much better, especially for very low flow rate wells. Now the third type of spinner is what we call the Petal basket flow meter, which is a flow meter that you are using while taking a station. You cannot move the tool. If you have very low flow rates, something less than 100 barrels per day, 80 barrels per day or so, a normal spinner will be very difficult for it to distinguish the contribution. The only way to increase the speed of the fluid inside the borehole is to funnel the fluid and force it to pass through a small area so that you can have a spinner inside to sample that. This is done by having something like umbrella, making isolation inside the casing ID and forcing the fluid to go through this small funnel and go through the small spinner that we have inside there. Now, most of the people are using the spinner tool to measure their flow rates and the flow profile. And as I mentioned before, the amount of revolution per second from this spinner is proportional to the amount of differential or the relative speed between the tool and the flow. Let's imagine that we have a fluid moving upward and the tool is moving downward. So the relative speed will be the summation of the two velocities. If the tool is moving up and the fluid is moving up as well, then the relative speed will be the subtraction of the two fluids there. Now, to do the what we call the Insitu spinner calibration, we make our program with the following way. We make 4 up passes and 4 down passes, each pass at a constant speed, and we see the relative or the response of the spinner between perforations. So in front of the perforation, you will have some turbulence. So we do our interpretation in between perforation, and we call that interpretation zones. Let's look at this graph here. Now, the bottom perforation, below that we have what we call the zero flow. So area number A is what we call the zero flow. In between perforation, we take some interpretation zones to plot our spinner versus cable velocity, and at the top, this is what you have the full flow. So we plot in the x-axis the cable velocity, and in the y-axis the spinner RPS, and we start to plot at each zone the different float velocities up and down and the response of the spinner, and hopefully those should come to a straight line. Once we get this is a very good indication of quality of the log. If you merge all the spinners together, they should follow each other because the response or the contribution from each perforation is constant if the well is at steady state condition. So once we have straight lines, we'll be able to calculate the fluid velocity out of the spinner in situ calibration. Now, if we have single phase flow, like a well producing only oil, or a well with water injection, so only one fluid is there, so all you need really is this spinner calibration, and you'll be able to calculate the flow rate. Once you get your float velocity, you multiply that by the casing ID with some conversion factors, you'll be able to come up with how much barrels per day that you'll get. Now, the interpretation is done in a cumulative way, which means in the bottom zone, you get the zero flow, which means there is no contribution. Above the bottom perforation, you get the contribution of the perforation number 1 in the bottom. Above the second perforation, you get the cumulative contribution of both perforations 1 and 2. And above the third perforation, you will get the the contribution of the three perforations together. So if you want to get the individual contribution of a single perforation, you have to subtract above from below to get the contribution there straight away. Now, single phase interpretation is rather simple, and it doesn't take really that much long time to do in the field. And usually during the course, we give lots of examples for the audience to practice and do this interpretation. Now, if you go to two-phase flow, like oil and water, oil and gas, water and gas, then we really need to have extra information to subdivide the total flow rate into how much oil, how much water, or how much oil and how much gas, and so on. This is done through what we call a fluid holdup. So what is a fluid holdup? A fluid holdup is the percentage of each fluid at a specific cross-section of the casing ID. This holdup has nothing to do with the water cut at surface. So if you can have water holdup at the bottom between perforations of 40-50%, but at the top you'll have water cut of 10 or 20% only. So water cut and water holdup, they do not equal each other at all. Now we have several tools that can measure the fluid holdup in the borehole. We'll just mention a few of these, and during the course we'll go very thoroughly through each one of these. The first one and the oldest one is the Gradual Manometer. So what is the Gradual Manometer? It's a tool that measures the fluid gradient between two fixed points in the tool separated by 2 feet. By measuring the differential pressure between those 2 points and going through a small equation, we'll be able to get what is the density of the fluid between those two ports. Now, this density is measured in gram per cc. The total response of the Gradual Manometer is the density of the water multiplied by the percentage of the water plus the density of the oil downhole multiplied by the percentage of the oil downhole. If I know the oil density and the water density downhole, then I'll be able to get my percentage of oil and water downhole straight away from Gradual Manometer measurements. Now we have other tools that can measure the fluid holdup downhole. One tool is called the Nuclear Fluid Density, NFD. This tool is having a small radioactive source, gamma ray source, which is very similar to the gamma ray source inside a density tool in the open hole, with very short spacing between source and receiver, or source and detector. And we measure the fluid density around the tool with the fluid surrounding the tool there. The measurement is good, but unfortunately we have two main disadvantages. One is that we have to put a natural radioactive source inside the tool. So not so many people will be brave enough to accept that, because if something goes wrong and we have to leave the tool in the hole, you will leave a tool with a source which is alive for the next 200 years. And nobody really wants to do that. Second, this tool has to be very well centralized, because if it is slightly excentralized, coming very close to the casing ID, you will be measuring the density of the fluid with a little bit proportion of the casing density as well, which is steel, which is very high. So you will end up having something which you really don't need to measure. One thing to mention here, that for the Gradual Manometer measurement, you cannot do it in a horizontal well or highly deviated well, because in a horizontal well you will not have pressure differential there. So the physics collapses completely. The third tool that we can use for measuring the water holdup really is what we call the capacitance tool. A capacitance tool is a tool with two plates with high voltage potential difference between them, and whenever the fluid passing between those two plates, like a capacitor, the frequency of the resonance changes, because the water has different resonance frequency than the oil, than the gas. So this tool is mainly for water holdup. Unfortunately, if the water holdup is more than 30 to 40%, the response saturates. So you will end up having the same holdup. If it's 30%, 40%, 50, 70, 80%, you'll have the same answer there. So it's not good for high water rate wells. Several other sensors exist that we are using inside the PLT, the advanced PLT tool. We'll discuss it as we go to horizontal wells. Now in horizontal wells, we have to take care of the way the fluid is moving. Most of the time the fluid is moving in a stratified pattern, which means that the lower side of the hole will have the water flowing, the upper side of the hole you will have the gas flowing, and in the middle somewhere you will have the oil flowing there. These three different fluids are moving with three different velocities, and the aim on horizontal well is to physically measure each phase flow or each phase velocity there in feet per minute. Now, if you put a normal spinner inside the horizontal well, you will not be able to sample everything. There is no way. You will not be able to sample the three fluids that are passing through the ID of the casing. So we have different tools, and we'll discuss that during the normal course, of different technologies that exist from different vendors. One of them is the FSI, which is a flow scanner imager that has 5 different mini spinners and 5 other sensors associated with it to measure the holdup. One of the holdup sensors associated with this tool is what you call the DIFT, Digital Entry Fluid Tool. The main physics of measurement, without going into too much details, is the resistivity of the fluid. If the fluid is water, salty water, then it will be conductive, so it will conduct electrical current. If the fluid is oil or gas, it will not conduct current. So it's either yes or no, on or off, 1 or 0. In this case, you'll be able to get the water holdup from a very simple digital flow meter, digital resistivity tool there. The other sensor that we have inside the FSI is what we call the GHOST, gas holdup optical sensor. How this is working, it's mainly for gas holdup. We emit a light beam from the tool, and whenever this light goes through water or oil, it will just penetrate and go. If it sees a bubble of gas, it will reflect and come back again to the tool itself. The tool will measure the amount of light received back from the fluid. If you have high reflectivity, this means you have high gas. Low reflectivity, then you have low volume of gas in front of the tool. And by this way, we'll be able to see the gas holdup. So the DIFT is for water holdup, and the GHOST is for the gas holdup. And how can we get the oil holdup? 1 minus the other 2 together. This will be our holdup, because the total summation of the holdup should be 100%. Now, once we get our flow profile with how much oil, how much water, how much gas is coming from each perforation, and we draw that in a nice chart, then we'll be able to decide what do we need to do. If you have extra water coming from a specific perforation, we need to plug it back. If you have one perforation that is not producing as per expected open hole logs, then we need to see how we can improve that. Do we need to reperforate? Do we need to acidize? Do we need to do this or that? We have to decide based on the flow profile that we see from the production logging survey that we're running there. Spinner and gradual manometer are very important to get the flow profile, but we have extra sensor as well that can be used for other things, like a temperature sensor. It's very important to have a temperature profile of the well flowing, so that you'll be able to have a backup measurement of flow. For example, if oil is flowing from a certain perforation, it will heat up the borehole compared to a static temperature survey. So we run temperature survey with the well flow, with the well shut in first. This is our baseline. Then we compare it with the flowing. If the temperature is increasing between the flowing and the shut in, this means that we have extra flow coming from the oil, because the oil is coming hot and it's heating up the borehole as it goes up. The inverse of that will be gas. If you have gas coming from a perforation, gas, when it expands, it cools down. So temperature will drop in front of gas production there. This will give us a good idea about what do we have downhole. And the beauty of that even if this flow is coming from behind the casing, temperature will be able to see that as well. Last but not least, one of the very important sensors inside the production logging is the pressure. And we all, those reservoir engineers and production engineers, they know that pressure is very important. You need to know how much is the flowing pressure downhole. Pressure will give you an idea of how stable the flow rate is. If the pressure is stable at a specific interval versus time, then the well is flowing steadily. If the pressure is fluctuating up and down, then the well is not steady yet, and we have to wait till the flow rate is steady. Last important thing about production, pressure measurement, is that once we finish the survey, we can shut in the well and we start to record pressure buildup. And from pressure buildup analysis, we'll be able to get pressure transient analysis, which will help us to get formation permeability, formation skin, distance to the nearest boundary, and so on. And I'm sure most of the reservoir engineers will be more familiar with that. Now, this was a quick illustration of what we are delivering in production logging interpretation and logging. You will not be an expert after you attend this course, but you will be having the right tools and the right techniques so that you can use in the future. Once you finish the course, you don't go back to your location or base and throw the material away and say, okay, fine, I have attended the course. No, you will have to physically use this material to grab some logs, get some logs from your location. I'm sure everybody will have access to some logs. Get some production logs, get some cement evaluation logs, get some corrosion, get some TDT, RST, and start to interpret yourself by your hand. And during the course, as I mentioned, we have lots of exercises, and you have to do it by hand. And you will make mistakes, and you will discover your mistakes, and you will end up not repeating those mistakes in your real life. With that, I would like to thank you very much for attending this very short presentation. And I hope that maybe in the near future, since we are all working from home right now with the coronavirus spread, maybe you can deliver another topic in the near future, inshallah. Thank you very much, and have a good day, and have a safe day with your families. Thank you very much. Bye-bye.